Quantum computers have long been described as machines that could transform science, medicine, cybersecurity, and our understanding of reality itself. Now, Google's latest quantum processor, known as Willow, has brought these ideas back into the spotlight. Not because it proved the existence of parallel universes. Not because it opened a gateway to other dimensions. But because it demonstrated just how different quantum computation is from anything classical computers can achieve. Willow is a 105-qubit superconducting quantum processor designed to advance one of the greatest challenges in the field: quantum error correction. Quantum systems are extraordinarily fragile. Tiny vibrations, stray electromagnetic fields, temperature fluctuations, and even cosmic radiation can disturb quantum states, causing calculations to fail. Overcoming this problem is essential. Without reliable error correction, large-scale quantum computers remain impossible. Google reported that during specialized benchmark tests, Willow completed calculations that would be extraordinarily difficult for today's most powerful classical computers to reproduce using currently known methods. These experiments do not mean quantum computers are already replacing everyday computers, but they do demonstrate a remarkable difference in computational capability for certain tasks. To understand why, we must first understand how quantum computers work. Traditional computers process information using bits that exist as either zeros or ones. Quantum computers use qubits, which can exist in combinations of both states simultaneously through a phenomenon called superposition. When qubits become entangled, their properties become connected in ways that have no direct equivalent in classical physics. This allows quantum algorithms to explore mathematical possibilities much more efficiently for specific problems. However, popular descriptions can sometimes be misleading. Quantum computers do not simply try every possible answer at once. Instead, they manipulate probability amplitudes so that correct solutions become more likely while incorrect possibilities cancel out through interference. This process follows the laws of quantum mechanics with extraordinary precision. And that leads to a deeper question. What is actually happening during a quantum computation? For more than a century, physicists have debated the meaning of quantum mechanics itself. The traditional Copenhagen interpretation suggests that quantum systems exist as probability waves until measurements produce a single observed result. Another idea, the many worlds interpretation, proposed by physicist Hugh Everett in 1957, offers a more radical possibility. According to this interpretation, every possible outcome continues to exist in separate branches of reality rather than disappearing. Some researchers, including physicist David Deutsch, have argued that quantum computing fits naturally within this framework. Yet an important distinction must be made. Interpretation is not evidence. Google's Willow processor has not detected another universe. It has not communicated with parallel realities. It has not proven the existence of a multiverse. The many worlds interpretation remains one of several scientifically valid explanations of quantum mechanics, but no experiment has yet determined which interpretation correctly describes reality. What Willow has done is make these philosophical questions feel more tangible. Quantum mechanics is no longer just a theory written in equations. It is becoming a practical technology. Equally important is Willow's progress in error correction. For decades, researchers understood that useful quantum computers would require many physical qubits working together to create stable logical qubits. Google's results suggest that increasing the number of qubits can reduce errors rather than increase them, a critical step toward fault-tolerant quantum computing. This may prove to be Willow's greatest achievement. Reliable quantum computers could one day transform drug discovery by simulating molecules with unprecedented accuracy. They could accelerate the development of advanced materials, batteries, superconductors, and catalysts. They may improve optimization problems in transportation, manufacturing, and logistics. Quantum computing could also reshape cybersecurity because future machines may challenge current encryption systems, leading governments and companies to develop new forms of post-quantum cryptography. Even so, experts agree that large-scale practical quantum computers are still years away. Significant engineering challenges remain. But the progress is undeniable. Perhaps the most fascinating aspect of Willow is not that it answers humanity's deepest questions. It is that it encourages us to ask them again. What is the true nature of reality? Why does quantum mechanics work so perfectly? Are probability waves fundamental, or is there a deeper explanation still waiting to be discovered? As quantum processors evolve from hundreds to thousands, and eventually millions, of error-corrected qubits, they may transform technology in ways we can barely imagine. At the same time, they may deepen one of humanity's oldest mysteries. How is reality itself organized at its most fundamental level? Whether future discoveries support the Copenhagen interpretation, many worlds, or an entirely new framework, one fact is already clear. Quantum mechanics is no longer merely an abstract theory. It is becoming a powerful technology. And processors like Willow are helping humanity explore not only the future of computation, but also the hidden structure of the universe itself. As impressive as Willow's performance is, its greatest achievement may not be speed at all. The real breakthrough is quantum error correction. Unlike the transistors inside a classical computer, qubits are incredibly fragile. Even tiny vibrations, microscopic temperature changes, or stray electromagnetic fields can disturb their quantum state and introduce errors. For decades, this has been the biggest obstacle preventing quantum computers from becoming practical. Google's latest results suggest something remarkable. As engineers increased the number of physical qubits, the overall error rate actually decreased. That may sound simple, but for quantum computing, it's a major milestone. It shows that larger quantum systems can become more stable instead of less reliable, bringing scientists one step closer to fault-tolerant quantum computers. So why does this matter? Because reliable quantum computers could revolutionize fields that affect everyday life. Scientists could simulate complex molecules with incredible precision, speeding up the discovery of new medicines and life-saving treatments. Engineers could design stronger materials, more efficient batteries, and even new superconductors that dramatically reduce energy loss. Complex optimization problems in transportation, manufacturing, and supply chains could be solved far more efficiently than today's computers allow. Quantum computing may also transform cybersecurity. Future quantum machines could eventually break some of today's widely used encryption methods, which is why researchers around the world are already developing post-quantum cryptography designed to protect digital information in the decades ahead. But perhaps the biggest mystery remains philosophical. Willow has not proven parallel universes. It has not discovered another dimension. And it has not confirmed the many worlds interpretation. What it has shown is that quantum mechanics describes nature with astonishing accuracy, even though scientists still debate what those mathematical equations truly mean. As future quantum processors continue to improve, they won't just build faster computers. They may help us answer one of humanity's oldest questions: what is the true nature of reality? Whether the answer supports the Copenhagen interpretation, the many worlds theory, or an entirely new idea that hasn't yet been discovered, one thing is already certain. Google's Willow represents a major step toward the future of computing, and perhaps, one day, a deeper understanding of the universe itself.